Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture series in bioenergy. Let us start with the efficiency of these gasifiers. Okay, that is our next section, what we are going to be dealing with. So, this particular part will come with the title of this will be operation and performance of fixed bed gasifiers. Operation and performance of fixed bed gasifiers. Okay. So, the first point to remember out here, it is a very simple design, and this is the very first one which were utilized by mankind. Simple design, there is no complexity. By this time you must have seen. So, you have the feeder, you have the drying zone, you have the combustion zone, then you have the airflow, and you have ash collector, and you have a gas output. So, you have devolatilization zone, you have reduction zone, you have a combustion zone, you have a feeder. So, it is a very straightforward simplistic model of gasifiers. So, it is a very simple design and easy to develop and easy to work and do a lot of research on these kind of things, as well as for the production unit. This is the first property. Second, generally these kind of fixed bed gasifier gives you low, this downward arrow indicates low calorific value of gas. Okay. And they have higher concentration of tar. This is upward arrow showing higher concentration of tar, and this particular part I am boxing it, this is a challenge. So, there is a lot of work which goes on to improve upon this. So, obviously CV or the calorific value, how we could increase it, and this one how we could reduce it. This is the most fundamental challenge what you face in these kind of fixed bed gasifiers. Now, third important point, what are the composition? What is really this, what kind of calorific values you get? It is around, if you remember in the previous class we have talked about megajoule per Newton meter cube. Okay. This is the kind of calorific value which is fairly low, and if you remember the natural gases we talk about, if you see this 4 to 6, you always have to compare with the natural gases which is around 36. So, which is at least 6 times more, or if not 6, if you are getting 4, it is almost like 9 times more efficient what you get from nature. Okay. So, currently what man can do is in the range of 4 to 6 using a simple design of a flat bed or a fixed bed gasifiers. Okay. So, now let us see, appreciate what are the concentration of this, the product gas what you are getting. Generally it is 40 to 50% of nitrogen, 15 to 20% of hydrogen, 10 to 15% of carbon monoxide, again 10 to 15% of carbon dioxide, CO2. You have 3 to 5% of methane, CH4. This is a typical concentration of product gas what you obtain by gasifying the feedstock or the biomass in a fixed bed gasifier. I mean, the number may vary here and there a little bit depending on if you are using downdrift or a updrift or a cross flow system. So, this is something what one has to appreciate, that this is the kind of efficiency we get, efficiency or calorific value which is fairly low, and this is the typical composition. Typical composition. Okay. Next important aspect is how one can increase. So, this is a challenge, how you can increase the CV or the calorific value. So, one approach is that you have to reduce down on the moisture level. So, reducing the moisture level to something less than 15 to 20% is a challenge, but as you people remember in the last class I said the very moment you wanted to do this reducing moisture level, so you are talking about energy input. And there are suggestions which have been made and which are being followed, energy needed. This can be achieved by using a lot of waste heat. Moisture level reduction could be done by waste heat, which comes out from gasifiers, waste heat. So, waste heat is a huge problem across the globe. There is a lot of waste heat which is being generated, which has no utility value. It is kind of thrown out into the environment. So, how we can utilize that waste heat? One of the approach is that you can reduce the moisture content by using this particular heat to reduce it down to below say 15%. That is one approach by which you can increase the calorific value of the system. Now, the fourth aspect which worth highlighting is that the energy content of the product gas, the energy content of the product gas, the energy content of the product gas is up to 75% of the biomass energy content of the biomass energy content. Okay. The loss being accounted for. So, where are we having the loss? The loss being accounted for, loss being accounted for by the sensible heat in the product gas, either by the sensible heat in the product gas, one way. Second is the heat content of the ashes, the heat content of the ashes, and third is there is huge amount of radiation loss. So, while discussing this, if you go through these 3 points, one thing which will definitely strike, we need strategies to utilize the waste heat. There is a lot of radiation loss in most of the engines what we are using. There is a huge amount of loss, sensible heat loss. There is a lot of heat which is being absorbed by the ashes which is getting lost. And if we have some way we could utilize it, transform that heat energy using some form of thermoelectric materials where you can use the heat to generate electricity, it could be a very big asset. In a small capsule which I will be covering at the end, I will show you one of the technologies what we have developed where you can use natural fibers which will absorb the waste heat and convert it into electricity. So, this area not only one has to think how we can increase the efficiency of the system, how we can really do a better level of methane and everything. One has to keep in mind these are very robust system which generates tremendous amount of heat energy. If some way or other we can translate some of those heat energy, one can make tremendous difference, and that we will be highlighting in the later half. Just remember this part, like we are not done with it. We will come to this where we will be talking about how to waste heat management. A small capsule I will be adding, okay? Waste heat to electricity. This will be coming at the fag end, okay? So, now after this, the next point which is worth highlighting here is that in addition to the initial release of volatiles, a solid char residue is produced termed as charcoal. It produced from this char can be reacted further to have additional. What does this mean? So, during these process you are developing lot of charred products, and those charred products mostly go as a loss or as a waste. But there are technologies by virtue of which we can do further processing of the char to develop some really high efficiency good quality gas. So, this is what we are highlighting here. So, coming back, in addition to the initial release of volatile, initial release of volatiles, a solid char residue is produced, okay, which is also termed as charcoal. Termed as charcoal if produced from wood or coal. Interestingly, this char, what you are obtaining is these charcoal or this char, the solid char, this solid char what we are talking about, this solid char can be reacted further, okay, can be reacted further to produce additional gases. So, this is another aspect which is worth considering, that could we consider these kind of charred materials further processing by virtue of which we can generate gas and store it. Now, we will come to the last point about this fixed bed reactors or flat bed reactors. How we can increase the efficiency of the system. Back in 1995, almost 20 years now, a little more than 20 years, ideas have been proposed that if we do this whole process in two different stages, we can increase the efficiency. So, let us highlight what does that mean, what it means in two stage of combustion. Okay. So, this is what has been proposed. Okay. So, further improvement. So, for further improvement of the gas quality by operating this is the take home message, two-stage, two-reactor process, two-stage, two reactor process. So, what we meant by two stage two reactor process. Okay. So, this design which has been proposed is slightly more cumbersome, but it produces much higher quality of gas. So, let us divide it into two parts. So, okay. So, these are the two stages we will be talking about, stage 1 and stage 2, okay, S1, S2. So, the first thing what is being recommended here is what you do is pyrolysis of the biomass takes place in the first stage. So, pyrolysis of the biomass taking place at the first stage, at the first stage, okay, using external heating, So, you are kind of breaking up the molecules at 600 degrees centigrade, which is reasonably low. So, you look at it. No. So, next in this stage what is being talked about is I told you the two stage two reactor is going on. Okay. So, there will be 4 different stages we will be dealing with. The gases formed during this pyrolysis process in this stage 1A. So, A is this section, okay, A. Okay, so, that is why I wrote S1A. Okay. You see that S1A are reacted with steam to crack the tar, are reacted with steam to crack the tar. As I told you, the tar is a huge problem. So, what you are doing is the cracking the tar. So, what you did, you took the raw material, externally you pyrolyzed it, lack of oxygen. Okay. So, you could pretty much create lot of cracks in all over the structure, lot of rearrangement, and after this rearrangement what you do, the gas which is getting liberated consists of lot of tar. So, you put a high steam, as you know, it has a very high temperature, you pass a steam through it. What steam will do, because already the structure is kind of cracked up, it will embed into it and it will further crack the whole tar which is getting generated. You remember I told you in previous say that you can actually convert the tar into high quality gases, but you need technologies. Okay. So, now this is stage B of stage 1. So, this we number it as B. So, this is S1B. Now, what you do, what is getting generated out here, you take this. Now, we are starting the stage 2. So, I told you 2 stage 2 reactors. Okay. So, gases react with the char, gases react with the char from the first stage or S1 to produce the final product gas, to produce the final product gas. And this product gas is further, the last stage is further went through a cleaning up. And if with certain degree of energy efficiency this is achieved, then this is good enough to spark a ignition gas engine. So if you look at in light of the chemistry what you are doing, you are essentially, if you remember those 4 reactions what I taught you in the beginning, if you understand the chemistry, what the researchers are suggesting is that you do those reactions at separate level. So instead of processing the whole thing in one combustion unit, you split it up. You first of all do the pyrolysis, pick up the gas into it, that gas reacted with the steam, further break up the tar, then use that gas which is formed with broken up tar, you produce the next level of gas. So in that whole process, and at the end you clean it up. So this is one of the strategies which has been suggested fairly late, around 1995-96, almost 20 years, and people are working towards it in order to increase the efficiency of these kind of reactors. So having said this, let us once again go through where we started with the gasifier. That will kind of help us to revise the whole thing. Okay. So we talked about the fixed bed gasifiers. As I told you, it is a very traditional process and functions at around 1000 to 1400 degrees centigrade, as you could see, and it is classified under updrift system where the air is coming from bottom and going up. Let us again look at it. Okay, air is coming from bottom and going up. The next, and by the way, in the updrift, the gas which is coming out is at a much more lower temperature. It is almost the same temperature as the drying zone, 200 degrees centigrade, where it started likewise. Okay. So if you mark it here, asterisk, you mark it here, you kind of see the temperature, okay, around 200 degrees centigrade. Then we talked about the downdrift gasifiers. In the downdrift gasifier, so if I had to draw here, so what is happening with respect to T degree centigrade, it is started like this and move and comes back like this, right. And in the downdrift, if you look at it, the temperature, so this temperature is around 200, okay, and this is what we talk about 1400 degrees centigrade. So again same thing, here 200 degrees centigrade, here 1400 degrees centigrade, and if you look at it here, the temperature is like this. So you see there is a shift, there is a very interesting shift which took place, okay, and similarly in the cross flow, even it is much more steeper. So if it is 200 degrees centigrade and 1400 degrees centigrade, so you will see it is even much more. So efficiency wise, in this case, in the updrift, you are getting a gas back at 200 degree, which is the most efficient one. Here you are getting a gas around 1000 degrees centigrade, 900 to 1000 degrees centigrade, which is slightly lesser efficient, and this one is maybe near to downdrift or maybe less than downdrift. Okay. And the other area where this whole thing happens is the tar concentration. So in the downdrift, if you remember, your tar is low, whereas compared to here tar is higher, here also tar is higher, but here particle is higher. So overall it is always a big trade off. You cannot have the best under the sun. You will always have to do a trade off between the two. So this is in summary, if you look at it, this is what we have undergone, and we have talked about the design of these reactors, downdrift, updrift and the cross flow reactors, and we talked about all the basic fundamental properties of these gasifier, and in between we talked about the composition, the typical composition of 40 to 50% nitrogen, 15 to 20% hydrogen, 10 to 15% carbon monoxide, 10 to 50% CO2, 3 to 5% CH4. So now if some way or other you can increase this percentage, you are going to improve this number, which, as you remember, again just to highlight, for natural gas, if you are comparing with natural gas compared to naturally available gas from natural gas wells, which is around 36 megajoule per Newton meter cube, whereas man-made ones using a fixed bed reactor is around 4 to 6. So the take home message is that there is no optimal design. When you will be in the field, you will be running industry of bioenergy production or gasification, there cannot be any uniform thumb rule. What you have to do? You have to understand these basics. Based on that, you have to see your feedstock, what you will be using, or the biomass, what you will be using for gasification, based on its basic fundamental properties. So you guys remember when we talked about in the beginning of this section, the basic properties what has to be dealt with, the feedstock properties, the moisture content, ash content, volatile compound and particle size. Based on these things, the feedstock properties, and keeping in mind these critical things, what kind of treatment has to be given, one has to optimize. So your feedstock treatment, which is the most fundamental basics of it, which we covered in the section C, and you have to remember always the basics. So again, this is that comparison. So we are at this point out here, 4 to 6 megajoule per Newton meter cube, okay, and always remember these 4 reactions. This is very, very critical. These 4 reactions should be your guiding principle. This one, this one, this one, and this one. Water gas shift reaction, methane production, partial combustion to form CO between carbon and half oxygen or lack of oxygen, or a complete combustion by C plus O2. These 4 reactions should be always in your tips whenever you are doing these kind of science. If you know these and you know the nature of the biomass or the feedstock, and if you cleverly or wisely design the pre-treatment strategies and you have a fair knowledge about the gasifier designs, one can really harvest a lot of energy from these kind of biomaterials. Okay. So with this section, now after this we will move into the fluidized bed reactor. So I will close in here. Please go through it, keep the chemistry in mind, keep the properties of the biomass in mind, and then things will be very clear to you. Okay. Thank you.